For most of their history, railways were protected by physics. Steel relays, mechanical interlockings, wires you could touch. A signal was safe because it was a physical object, sealed off from the outside world. That world is gone. Today's railway runs on data, software, and radio. And anything that runs on data can be attacked. This is the story of cybersecurity and AI on the modern railway. It's really two stories at once. On one side, artificial intelligence is making railways smarter, predicting failures before they happen and running trains closer together than ever. On the other, connecting everything to everything has opened a vast new attack surface, exposing safety-critical systems to hackers. Opportunity and threat tangled together, and both, now, are part of railway safety. Start with the shift that made all this possible. Old signaling was built around an air gap. The systems that moved trains were physically isolated, with no wire connecting them to the internet. But modern traffic control streams data from thousands of trackside sensors up to corporate networks and the cloud. That air gap has been dismantled. The railway's control systems are now just another network, and networks can be reached. To manage that risk, engineers organize the railway into layers, using a framework called the Purdue model. At the bottom are the physical devices, switches, track circuits, brakes. Above them sit the interlockings and onboard computers, then the regional control centers, and finally the enterprise IT and the cloud. Between each layer sits a controlled boundary, a conduit, meant to let data flow up while blocking commands from flowing down. The danger is when those boundaries are bypassed. If the network isn't properly segmented, malware from an infected ticket machine or public Wi-Fi can move sideways, then down, all the way into signaling. Worse is what engineers call shadow OT. Crews quietly plugging rogue cellular modems into remote signaling houses to save a trip. Each one is an unguarded backdoor, wiring a safety-critical interlocking straight to the open internet. But first, look at what all this connectivity buys you, because the upside is enormous. The biggest prize is maintenance. Traditionally, parts were replaced on fixed schedules, whether they needed it or not. Safe, but wasteful, scrapping good components while still missing surprise failures. AI changes the question from how old is this part to how healthy is it right now. This is predictive maintenance, and it runs as a continuous loop. Sensors on bogies, axles, and switches stream vibration, temperature, and current data to edge computers. Machine learning models analyze it, estimate each component's remaining useful life, and automatically raise a work order, but only when the data says the part is genuinely degrading. Sensors, to analysis, to prediction, to action, and back again, around the clock. The clever part is how the AI spots trouble. Models called autoencoders are trained only on what healthy equipment looks like: normal vibration, current, and heat. When a live sensor stream starts to drift, the model can no longer reconstruct it cleanly, and its error spikes. That spike is the early warning, a fault flagged weeks before any human could see or hear it. Computer vision, meanwhile, scans inspection footage for microcracks in the rail. You can picture it as a health curve. A component starts healthy, and for a long time its condition holds steady. Then degradation begins, subtle at first. That's where the AI raises an anomaly. From there, the model forecasts the slope down to the functional limit, the point of failure. The gap between the anomaly and that limit is the whole prize, the window to act, on your own schedule, before anything breaks. Feed all of this into a virtual copy of the whole railway, a digital twin, and operators can simulate stress and schedule work when disruption is lowest. This isn't a lab demo. In 2024, the Copenhagen Metro rolled out exactly this kind of platform across its trains, tracks, and power substations, moving from rigid inspection routines to real-time, network-wide maintenance. The same pipelines even point toward fully autonomous operation. Now the other side of the ledger. Every one of those data links is also a way in, and here's the uncomfortable truth. Many core railway protocols were designed decades ago for safety and speed, not secrecy. They often carry no encryption, no authentication, no way to prove a message is genuine. To such a system, a forged command and a real one look identical. So why is a hacked signal so dangerous? Because the train believes it. Take the Eurobalize, the transponder between the rails that tells a train its position and speed limit. As the train passes, the police sends up a telegram, and the onboard computer trusts almost any packet that passes a simple error check. There's no cryptographic signature, so an attacker with a cheap software-defined radio can record a real telegram, then replay it carrying a false, higher speed limit, and the train, trusting it completely, could accelerate into an overspeed. Urban metros face a different trick. Communication-based train control keeps trains talking constantly to trackside radio over ordinary Wi-Fi, and Wi-Fi's management frames are sent in the clear with no authentication. An attacker, even a passenger with a laptop, can forge a deauthentication frame that impersonates the access point and knocks the train off the network. Lose that link for over half a second, and the failsafe slams on the emergency brakes. One laptop can freeze a whole line. The pattern repeats. America's positive train control leans on radios from a single supplier, so one firmware flaw could ripple across the whole national network. And the barrier keeps dropping. Cheap software-defined radios let attackers jam or spoof signals from beside the track. Defenses are catching up, focusing the signal into leaky cables along the rails and hopping frequencies to dodge a jammer. But the root weakness is legacy radio that simply trusts too much. And none of this is hypothetical. Over the last 2 decades, real attacks have moved trains, halted fleets, and turned rail into a target of geopolitics. The methods range from a teenager with a modified remote to state-linked operations, but the lesson is consistent. You don't need to breach a locomotive's computer to cause chaos. Sometimes the oldest, simplest link in the chain is the one that breaks. Poland, August 2023. Attackers used a software-defined radio worth about $30 to broadcast 3 simple tones on an old, unencrypted frequency. That tone sequence is the railway's radio stop signal, and any train that heard it triggered its emergency brakes. Around 20 trains ground to a halt, the broadcasts laced with the Russian national anthem. No firewall was breached. The system simply had no way to ask whether the signal was real. Denmark, 2022. This time, nobody touched the trains at all. Criminals hit a third-party contractor, Supio, with ransomware. In response, Supio shut down its own servers, taking an app called the Digital Backpack offline. Drivers rely on that app for real-time safety data, and by law they can't run a train without it. So the whole national fleet stopped. A ransomware attack on a supplier had paralyzed an entire railway, indirectly. Belarus, 2022. A hacktivist group encrypted the railway's routing and scheduling databases and disabled its automatic train control, aiming to slow Russian military transport heading toward Ukraine. The railway fell back to manual, paper-based routing, crawling at 15 to 20 kilometers an hour for weeks. Tellingly, the attackers deliberately avoided the safety-critical braking systems. Proof these tools can be aimed with precision for coercion rather than carnage. And it isn't only sabotage. In the UK, an insider defaced the public Wi-Fi at 19 stations, and a separate ransomware crew forced a transport authority into a recovery costing tens of millions of pounds. Add it all up, and the weak points are always the same. Legacy radio, flat networks joining office IT to signaling, third-party suppliers, and trusted insiders. So how do you defend a railway? Not with a single wall, but with defense in depth, many layers, each assuming the one before it might fail. It starts with segmentation, carving the network into security zones, connected only through tightly controlled conduits. The most consequential systems, interlocking, breaking, are ranked by the harm a failure could cause, and walled off the hardest. At the most critical boundaries, engineers use a data diode, a gateway that is physically one-way. Diagnostic data can flow up from the tracks to the analysts in the cloud, but no command can ever travel back down that path. Safety-critical control messages, meanwhile, run over protocols like Rasta, which send every message twice, over 2 separate channels, so a single cut cable or a burst of noise can't quietly corrupt a command. Then there's the supply chain, the soft underbelly of nearly every incident we've seen. Operators now demand a bill of materials for software and hardware alike, a full parts list of every component inside a system. So when the next big vulnerability lands, they know instantly what's affected. And because you can't always patch a safety-certified controller overnight, They use virtual patching, blocking the exploit's traffic at the zone boundary while the certified code stays untouched. Underpinning it all is a change in mindset, now written into standards like Europe's CLC/TS 50701 and the coming international IEC 63452. The core idea is simple. Cybersecurity is no longer separate from safety. It is safety. Every attack scenario gets logged alongside mechanical faults in the same risk registers. A hacked signal is treated as seriously as a cracked rail, because on a digital railway, they can cause the same thing. The modern railway is a paradox. It is smarter, safer, and more efficient than any generation before it, able to predict its own failures. And in the same breath, it is more exposed, its safety now resting on lines of code and pulses of radio as much as on steel. The challenge for the next century isn't choosing between the two.